Momentum is a way to measure how hard it is to stop an object, and it depends on two things: the mass of the object and its velocity. We calculate momentum by multiplying mass, which is how much matter an object contains, by velocity, which is the speed and direction the object is moving in. The formula looks like this: momentum equals mass times velocity, or P equals m times v. It's important to note that momentum is a vector, meaning it has both size and direction, which is why you see the arrows over the letters in the formula. The standard unit for momentum is kilogram meters per second, so when you multiply mass in kilograms by velocity in meters per second, you get the momentum measured in those units. This concept helps us understand how objects behave when they move or collide.
Momentum is a vector quantity, which means it has both magnitude and direction. In this case, the direction of momentum is the same as the direction of velocity, which is shown here by the arrows. The arrow labeled v represents velocity, and the arrow labeled p represents momentum. Both point in the same direction, indicating that momentum follows the direction of the object's velocity. This relationship helps us understand how momentum behaves when an object is moving. The change in momentum is calculated by subtracting the initial momentum from the final momentum, which we express as mass times the final velocity minus mass times the initial velocity. Here, u represents the initial velocity and v is the final velocity. When an object, like a ball, bounces off a wall, its momentum changes in one or more ways. This could happen because the speed changes, the direction changes, or both speed and direction change together. For example, if the ball hits the wall and bounces back, its direction reverses, and possibly its speed changes as well, which results in a clear change in momentum. This concept helps us understand how forces affect moving objects over time.
In a closed system where no external forces act, the total momentum before any interaction is equal to the total momentum after that interaction. This means the overall momentum remains constant because no outside force changes it. So, we say that the total momentum, P, of the system is conserved, reflecting the principle that momentum in an isolated system does not change over time. In an elastic collision, the total momentum of the objects involved is conserved, meaning the combined momentum before and after the interaction stays the same. At the same time, the total kinetic energy is also conserved, so no energy is lost to things like heat or sound. As a result, after the collision, the objects bounce off each other rather than sticking together or deforming. The directions and speeds of the objects change, shown here by how their velocities switch or reverse, but this happens without any loss in kinetic energy. This kind of collision is idealized and important when studying collisions that don't involve any permanent change to the objects involved. In an inelastic collision, the total momentum before and after the interaction remains the same, meaning momentum is conserved. However, kinetic energy is not conserved because some of it is transformed into other forms of energy, like heat or sound, or is used to deform the objects involved. As shown here, before the collision, the two objects move toward each other with initial velocities u1 and u2, but after the collision, they stick together and move with a common velocity, verse. This sticking together or deformation is what distinguishes inelastic collisions from elastic ones, where objects rebound without permanent change. So, while the momentum stays constant throughout, kinetic energy decreases due to the change in the objects themselves. In an explosion, a single object splits into two or more parts that move away from each other due to internal forces. Before the explosion, the system is one whole object with a certain momentum. After the explosion, the object separates into pieces that move in opposite directions, but importantly, the total momentum of the system remains the same as it was before. This is because the forces causing the separation are all internal, so no external forces affect the total momentum. Essentially, the momentum before the explosion equals the sum of the momenta of all parts after the explosion, ensuring momentum is conserved even as the pieces scatter. When we look at different types of interactions, momentum is always conserved, regardless of whether the collision is elastic, inelastic, or an explosion. In an elastic collision, both momentum and kinetic energy remain conserved, meaning the objects rebound without permanent deformation. In an inelastic collision, momentum stays conserved, but kinetic energy is not conserved because some energy is lost to deformation or heat as objects stick together or change shape. During an explosion, momentum is still conserved within the system, but the kinetic energy increases due to the internal forces causing the parts to separate and move apart more rapidly. It's also important to remember that momentum conservation applies in each direction independently, so we account for both horizontal and vertical components separately.